What I'd like to talk about is Bernoulli's equation. And so the progression that we've been making here is looking at trying to measure the velocity of a fluid as it flows through a pipe, let's say. And when we looked at the continuity equation, that was more like kinematics. You measure the velocity going into the pipe, you could measure the velocity going out of the pipe, but you weren't really looking at the cause of what's making it move. And in this section, we're going to look at the causes. So this is more, if you think of like Newton's second law, whereas the continuity equation was more like Newton's first law. And so what if we consider a volume which has a certain cross-sectional area right here, then there may be a force on, we'll call it the high side. So this is the side of high pressure. And this would be the side of low pressure. And there's going to be a force pushing on this side, which we'll call FL. So you have a high pressure side and a low pressure side. The pressures are just going to be the force divided by the area. Where the net force is going to be the high pressure minus the low pressure side. Okay, so the Bernoulli effect is one in which we have basically this flow of a fluid through an area like this. So you have an area A2 and an area A1, and on this side there's going to be a velocity of the fluid V1, a velocity of the fluid V2. What the continuity equation tells us, and then there's going to be pressure on one side, P1, and pressure on the other side, P2. What the continuity equation tells us is that if the area A1, let's say, is bigger than the area A2, then the velocity V1 is going to be smaller than the velocity V2. And if it's moving slower, then that's going to mean that the pressure is going to be lower on that slower side. So if the fluid is moving slower, it has a lower pressure. If the fluid is moving faster, it has a higher pressure. And that's called the Bernoulli effect. But let's look at this more quantitatively, or basically let's come up with an equation that we can use to calculate these pressures. So let me draw a very complicated pipe. One in which it has two areas, area 1, area 2. Fluid is flowing into the left side and out of the right-hand side. There is a force, F1, pushing on the fluid. The fluid we can think of as basically this volume right here, which basically has a length delta x1. The fluid over here in the smaller end has basically the same volume, but it has a different length, delta x2. And that implies that there's going to be a force, let's say we'll call it F2, and for the sake of argument we'll have it pushing into the pipe. So this is going to be, we're going to set up a low pressure and a high pressure side of the pipe. The thing that we're doing new, the thing that we're adding to this problem that we didn't have before, is that we now have a height differential. And so the A1, this volume is going to be at a height of Y1, and over here, this height is going to be at a height of Y2. So not only do we have forces pushing on the fluid, moving it through the pipe, and the pipe is changing its area, it's constricting from an area A1 to an area A2, but now we're going to add in gravity. We're going to allow gravity to act on this mass of fluid which is flowing through the pipe. So let's look at conservation of energy. So the change in the kinetic energy plus the change in the potential energy is equal to the amount of work done. So that's K2 minus K1, the change in the kinetic energy, plus U2 minus U1, the change in the potential energy, is equal to the work, which is work 1 done on the low side of the pipe, plus work 2, the work done on the high side of the pipe. So now let's plug in all of our equations. So we have for kinetic energy 1/2 the mass times the velocity 2 squared minus 1/2 the mass times the velocity 1 squared plus mass gy2 minus mgy1 is equal to the works being done. Work 1 plus work 2. So let's clean this up a little bit. We can take out the masses. So I have 1/2 the mass times the change in the velocity squared plus mgy2 minus y1 is equal to the work done. Now the work, or for first, the mass can be written as the density, which we're not going to change, times the volume, delta V, and the work 1 is the force 1 times delta x1, and the force is the pressure 1 times the area 1 times the length. And now the volume is equal to the area times the length. But we're not changing the volume, it's an incompressible fluid, so delta V is A2 times delta x2, the length there. Okay, so the last thing we didn't do is the work 2, the work at the other side of the pipe, and that's force 2 times delta x2, which is the pressure 2 times area 2 times delta x2, which means that work 1 is equal to the pressure 1 times the volume, and work 2 is the pressure 2 times the volume. However, if I go back to my drawing, I drew the force 2 in the opposite direction of force 1. So what I really should do is take into account the vector nature of the forces, and so this turns out to be minus pressure 2 times the change in the volume. Because we're looking at basically how these pressures, there's a pressure pushing the fluid in and maybe a pressure of the fluid pushing back on it. Okay, so now let's put it all together. We'll use our, we'll look at our energy terms, our kinetic and potential energy terms. So if I factor out the mass, I have 1/2 the change in the velocities, the velocity squared, plus g times the change in the heights is equal to pressure 1 minus pressure 2 times the volume. Now the mass, we said, was the density times the volume. So you can plug that in. So now you've got density times the volume times 1/2 change in the velocity squared plus g change in the heights is equal to P1 minus P2 times the volume. So the volume is the same on both sides, so we can cancel that. And now we can write this out fully as the density times, so 1/2 the density times V2 squared minus 1/2 the density V1 squared plus the density times GY2 minus the density GY1 is equal to pressure 1 minus pressure 2. So let's move everything around. Let's move all the subscripts 2 to the right-hand side and all the subscript 1 to the left-hand side. And so what I have is pressure 2 plus the density times the velocity squared divided by 2 plus the density g times the height is equal to pressure 1 plus the density times the velocity squared over 2 plus the density g times the height. And so what's interesting is that it doesn't matter which side of the pipe you're on. If you're on the left-hand side, which I called 1, or the right-hand side, which I called 2, then what you get is the same equation, that the pressure plus the density times the velocity squared divided by 2 plus the density times g times the height is equal to a constant. Or if you want to use this one up here, then this equation for one side of the pipe has got to be equal to the same thing on the other side of the pipe. Which really shouldn't be all that surprising. It's kind of a fancy equation with densities and pressures and velocities and heights. But really, we started this whole derivation with the conservation of energy. And so this equation, Bernoulli's equation, which is used to do things like calculate how an airplane wing is going to fly, or how a fluid is going to flow from the top of a building to the bottom of a building. If you ever want to if you have to work out the plumbing based on gravity, then it's not a surprising result because it's basically conservation of energy. So what you basically have is the pressure we got from the work. This term here with the velocity squared we got from the kinetic energy. And the density g times the height is just the potential energy. So really, Bernoulli got lucked out in the fact that he just used conservation of energy to come up with an equation which he could name after himself. Actually, this was before we actually solidified ideas of conservation of energy. So he actually did it in a much more elegant way. But I'm just showing that the principle of conservation of energy and work and Newton's laws comes together to give us Bernoulli's equation, which we can then use to calculate things like how fast something's going to move, given the fluid density, the height at which it's at, and the pressures that are applied to that object.